All right, now that we know how to work with the inverse operation of the square root in order to solve x squared, now we need to figure out a mathematical way to solve things that if we have x squared equals a negative number, what do we do there? So complex numbers are a way for us to solve any quadratic and get a mathematical answer. Let's look at what we know so far. If you took any number and squared it, so 2 squared equals 2 times 2, that's 4. If you took some other number, like negative 2, and squared it, you'd have negative 2 times negative 2. It has to be the same number when you square it, and you'd also get 4. If you took anything else, say you had 1/2 squared, lots of things with 2 here. What are we looking at? We're looking at 1/2 times 1/2. We get 1/4. So what happens is when you square things, no matter what the number is, whether it's positive or whether it's negative or whether it's a fraction, your answer, your result is always positive. So when you square real numbers, and I use real numbers in the sense of mathematics, and up until now, y'all are just thinking, well, real numbers, duh. When you square real numbers, these are numbers that you can graph. See and graph. Real numbers. You could put them on a number line. You could put them on an XY chart. When you square real numbers, the result is positive. Every time. And why is that? Because when you square something, you write it down twice. Two of them, either whether they're positive, we'll write it right here. Positive times positive, if it's the same number, they have the same sign, that's going to be a positive number. If you multiply a negative number times a negative number, that's also a positive number. So when you square real numbers, meaning you have two of the identical thing, the result is positive every time. And I'm making an emphasis there because this seems so obvious that you've not really thought about it up until now. But what happens if I tell you we're going to now solve something like x squared equals -1? Solve this. Is there a way that you can make a number inside of x squared that will give you a negative number? That goes directly against what I put right here. So how do we get around that? And mathematically speaking, we get around that with an imaginary unit, which we're going to call I. So mathematicians came up with I. It's equal to the square root of -1, and it solves all of our problems because it's a way that we can mathematically now answer something like x squared equals -1. So this is a mathematical workaround, basically, that lets us solve quadratics that are equal to a negative number. All right, so I've defined a new thing for you. I is the imaginary unit. It's equal to the square root of -1. I equals the square root of -1. It's not something you would see on a graph, not on a real number line graph. You can make an imaginary plane, but these are called imaginary numbers. Meaning it's the opposite of real numbers, what I'm talking about here. Real numbers you can see on a graph. Imaginary numbers you won't see on a graph. They are mathematical answers. They have real consequences. They change our graph. They change the shape of our graph. But we won't see them directly on real graphs. Now, this is titled complex numbers. So what is a complex number? A complex number is written as a plus bi, meaning this is some real number, this is real, and b is the coefficient of an imaginary number. So this is the imaginary part, and this is the real part. Complex numbers are always written separately. So written separately, which means that we're going to write the real plus or minus the imaginary part. So it's real plus or minus, depending on what b is, imaginary. And this will have consequences when we get to writing out fractions and some of our mathematical answers. The real number and the imaginary number are separate. So we won't write anything like this. We won't write 4 plus 3i all over 2. Instead, we would separate them and say this is 4 over 2 plus 3i over 2. Or even better than that, I guess we'd write 2 plus or minus, not minus. Sorry, I went a little further there. 2 plus 3i over 2. Okay, so we would not write it like this. We have to separate the real and the imaginary. So complex numbers. So 2 new things for you to be able to define. Imaginary numbers are mathematical answers. I is equal to -1. A complex number means a real plus or minus an imaginary number. And that helps us solve equations. So let's look at what that does for us. So in our last practice work, we did problems like this, where we said, if you have 2x squared plus 11 equals -37, how would you solve this? So hopefully you would look at this and go, there's just x squared. There's no x term, so I'm going to use the inverse to solve this. It's going to be easier than factoring. So how do we do that? We get x squared by itself. We subtract 11 from both sides. 2x squared equals -48. Before we take the square root of both sides, it's easier to simplify and get the x squared by itself. We'll divide both by 2. So now x squared equals -24. Okay, x squared can't be -24. There's no number that you can multiply by itself that would give you a negative number. So x squared means positive times positive or negative times negative. So what do? We're going to take this negative out when we write the square root of both sides with our plus or minus. That still is a thing. We're now going to say x equals plus or minus, and let's separate 24 into simplifying terms. We're going to call it the square root of -1. We're going to say 24 is 4 times 6. That gives us the negative part. The square root of 4 we know, the square root of 6 we don't, so we've separated it into things that we can simplify. Our final answer is x equals plus or minus, let's say the square root of 4 is 2. We normally write the I here, and then the square root of 6 we're going to leave on the end. Now, some professors, this is how we're going to write in Algebra 2. Some professors do prefer, as you get into college, the strict written separately like this, where I is in the very back. So some professors will prefer plus or minus 2 square root of 6 I. But sometimes the I looks like it's under the radical. I accept this if it's clear that it's not under the radical. If you write it like this, I accept it. It's fine. For our purposes, the I is clearly not under the radical here. But writing quickly, it can become 2 square root of 6 I, and nobody can tell whether this I is under the radical or not. So I need to be able to be sure that you took the square root of -1 completely out. It's no longer a square root. The I is all by itself. It represents the square root of -1. So what is this? This is a mathematical answer. If you graph this equation like we did on that one worksheet, this will not cross the x-axis. This is an imaginary solution. that we wouldn't be able to graph. So it is purely imaginary. But it gives us a way to solve this mathematically and find all of the roots of our equations. So I'm going to write down several for you to practice, and we'll come back and do them together. Okay, so for number 1, we're going to hit the square root of both sides. It's ready to go. X equals plus or minus. The negative becomes an I, and square root of 13 has no roots in it. There you go. You have two answers. One of them is plus I, the square root of 13, and the other is negative I, the square root of 13. So imaginary answers there. 2, x squared equals, subtract 11 from both sides. We have negative 8. Take the square root of both sides. I want to see all of that work and the plus or minus. That's going to be x equals plus or minus 8. It's going to be negative 1 times square root of 4 times square root of 2. So I'm taking 8 and rewriting it with the negative, the 4, and the 2. This is I. This is 2. I'm going to squeeze that in there. Normally we write the coefficient in the front. 2i, that's the 2, and then this square root of 2 has nothing, it stays a square root. Number 3, 3x squared equals, add 7, negative, what's that, 24? So, yeah, divide by 3, x squared equals negative 8, square root, x equals, don't forget the plus or minus. Again, I had square root of 8, so I'm going to say 2i square root of 2. This one, divide by 2, I've got that 8 again, got a theme going. X plus 3 squared. See, I only have x under the square, so I'm going to use the inverse method. I'm not going to try to multiply this all out. These cancel, I get negative 8, square root, plus or minus. Now the square and the square root in x plus 3 is free of the square. It's just x plus 3. I've got plus or minus 2i square root of 2 because we've done that several times. Now I need to move the 3 to the other side. I'm going to subtract it. X equals, negative 3 is just a number, and normally we write it in the front, plus or minus 2i square root of 2. So this is a binomial answer. It has the real part and the imaginary part separate. You can leave the plus or minus there. This is two answers to a squared problem. We have both of them. We're good. This is a mathematical answer, again, one that you will not see graphed, but it's a way for us to find answers for things that are equal to negatives, but they're squared. So this represents the answer. It's got a real part and imaginary part for number 4. All right, so now that we've been introduced to complex numbers and why we need them, let's learn how to do things with complex numbers. So we're going to add and subtract and multiply and divide with our complex numbers. And complex numbers work a lot like, in fact, exactly like terms with x's and y's. So let's look at some basic operations. Let's say we have 2 plus 3i plus 4 minus 6i. This represents, and the parentheses may confuse some people, but this represents two complex numbers added together. So this is the first complex number. It's real plus imaginary. Plus this complex number, which is real minus imaginary. So in order to find the new sum of both of these complex numbers, so these parentheses do not mean multiplication. They mean this first complex number compared to this second complex number. So in order to get the sum, we're going to add the real numbers together. So 2 plus 4 is 6. And we're going to add or subtract the imaginary numbers. We have 3 i's minus 6 i's. Altogether, that's negative 3 i's. So it's the same exact thing as adding or subtracting like terms. You add the real or subtract the real, and then you add or subtract the imaginary separate. So it's just like if you considered this to be an x, you would add the whole numbers together and then you would put the x values together. They work exactly the same way. The difference is when you get to multiplication. And so before I show you multiplication, I need to tell you what happens when you multiply an imaginary number times itself. So let's look for a second. In fact, I'm going to start a new page. So on my new page, I want to look at what happens if I have I. First of all, I by itself is -1, the square root of -1. So I to the first power equals I. That's not that exciting. But what happens if I say, what is I squared? Well, that means the square root of -1 times, I'm going to put my radical better, the square root of -1 times the square root of -1. And when you have squared square roots, it's just like the square root of -1 all squared. This cancels, you get -1. So I squared is always -1. I cubed means I squared times I to the first power. In other words, just like with x's, you add the exponents, you get I to the third power. Well, we've simplified I squared already, it's -1. And we know that I to the first power is just I, so this becomes -1 times I, or negative I. I to the fourth power is I squared times I squared, which we've already simplified as -1 times -1, and -1 times -1 is +1. Now we could keep going. I to the fifth equals I to the fourth times I. I to the fourth is 1. So 1 times I. This is I again. And then I to the sixth, we could call that I to the fourth times I squared. I to the fourth is 1 times I squared is -1. That's -1. So what happens is you have 4 possible answers with I to any power. They are, I'm going to write this more simply, I to the first power is I squared is -1, I cubed is -I, and I to the fourth power is 1. It's either going to be a flavor of I, positive or negative, or 1, positive or negative. And then after I to the fourth, it starts to repeat. So it'll be I to the fifth equals I to the sixth equals -1, I to the seventh equals -I to the eighth equals 1. And it would repeat again. You can probably stop writing. I to the 10th equals -1. So what do we know? We know that there's only 4 variations here. And you are going to need to put that in a box somewhere and probably on your note card for this test and memorize what I squared, I cubed, and I to the fourth is. But that box will tell you the power of I, what it's equal to for any power. So let's say we said I to the, something I don't have on my chart yet, what is I to the 15th power? So I to the 15th, and one way that students like to do this is just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I to the 15th equals I cubed equals -I. So you would simplify I to the 15th. It either simplifies to one of the ones or one of the i's to the first power. The other way to think about this is that 15, if you divide 4 into 15, it goes 3 times with a remainder of 3. That remainder of 3 tells you where it is on the chart. So it's in the third position. So it's going to be equal to negative I. So it goes around this little circle here 3 times, and then it lands on I cubed. Let's do a bigger number. Let's say we have, this will be A, let's say we have I to the 37th power. Well, we don't really want to count around the circle 37 times, but we know there are 4 variations here. So if we divide 37 by 4, 4 goes into that 9 times evenly. That's the amount of times it goes around the circle completely. And then where does it land after that? So that would be 36, subtract, we get 1 remainder. That means it would go around the circle 9 times, and then it would land on I to the first power. So this is I to the remainder if you divide by 4. So this is I to the first, this is just I. So every time that you have I to any power, I want you to divide by 4 and tell me what the remainder is. Let's do some more quick ones now that hopefully you believe in me. So let's say we have I to the, let's do 56 power. Divided by 4, that's I to the 1/14th power. And then we have a remainder of 0. Well, what is anything to the 0 power? That's also 1. So that still works, that mathematical conclusion. But it also means that it goes in evenly, it goes in to the 4th. It's going to be like the 4th, which is to the 1 power. So you also remember that I to any number to a 0 power is also 1. So mathematically speaking, either way you think about it, it works. Let's do I to the 102 power. Well, 4 goes into 100 25 times, and then 2 is left over. This is equal to I squared, which is negative 1. So it simplifies to negative 1. So anything that's I to any power always reduces to either a 1 or an I, positive or negative. So you can never leave an answer as I to the 56th or I to the 3rd even. If you get what is I to the 3rd, you have to reduce it and make it negative I. This chart you need to memorize so that you can simplify. Okay, we went through all of that just so we could do some multiplication. So we just did some addition. Let's just see that real quick one more time. Example 4, if you have 2 plus 3i minus 8 plus 2i, what does that mean? It means two complex numbers are subtracted from each other. We're going to use the same properties we would normally. Even though these are i's, we're going to distribute that negative, and then we're going to add the real numbers together. So that's negative 6, and 3 minus 2i is just I that's positive. So addition, subtraction are very simple. You add or subtract like terms. Multiplication gets a little bit more complicated, so let's look at it. So we have the same numbers, 2 plus 3i, but this times 8 plus 2i. So remember, the parentheses do not mean multiplication unless they look like parentheses that need multiplication. This one is subtraction because there's a giant subtraction sign there. This is multiplication because they're next to each other. So you do have to look. You can't assume that everything with parentheses is multiplication because it's not. This one is multiplication. We're going to FOIL just like we normally would. 2 times 8 is 16. 2 times 2i is 4i. 3i times 8 is 24i. 3 times 2 is 6. I times I is I squared. And now we have to use those rules from the box above. And that is that I squared equals negative 1. So we're going to change this to be negative 6. 6 times negative 1 is negative 6. So when you FOIL, you're going to get, you started with complex numbers, real plus imaginary. You're going to end with real plus imaginary because this I squared changed into a real number. It's just the opposite sign. 16 minus 6 is 10. 4i and 24i is 28i, and we have a new complex number that's real plus imaginary in the first degree that's our product. So multiplying these together gives us a product that's also a complex number. Be sure to notice when you have subtraction here or addition. Lots of students get it confused with multiplication because they see the parentheses. But the parentheses simply indicate this is complex number 1, subtract complex number 2. And the parentheses separate the real and imaginary for each one. Okay. So we've seen addition, subtraction. We've seen what happens when you raise I to a power. We've seen how to solve equations. The one thing we haven't seen is what to do if we have an imaginary number in the denominator. So let's take a look at that. It uses the same rules that we used in our last section. So sometimes we have to rationalize the denominator for imaginary numbers as well. So what does that mean? Well, that means that if we had example 1, like 3 over I, why do we have to rationalize that? So I is a square root. So this means 3 over the square root of -1, and that's not allowed. So we have to fix it so it doesn't have the square root of -1 in the denominator anymore. So our number 1 in the last section was if you have a monomial. If you have a monomial I in the denominator, that's the issue. You're going to multiply by I over I, and that's going to take care of it for you. Let's write out all the rules. So the second rule, and this I'm just going to write in one rule this time, is if you have a number over a binomial, so let's say we have 4 plus I, we're going to multiply by the conjugate. So this one's a binomial in the denominator. We're going to multiply by the conjugate. And that's going to be 4 minus 3i over 4 minus 3i. So those are our two rules simplified from the last section. This is a 3i. This is the identity property. This fraction with the same thing on the top and the bottom is equal to 1. This is equal to 1. We are just changing it around so that it no longer has I in the denominator. So let's do some examples like that. Let's start with a simple one that has just I in the denominator. Let's see. Example 6 is if we had, we'll just finish this one out. 3 over I. Oops. So 3 over I. Even if it didn't say anything, if it just said simplify, you have to know that I is a radical. Therefore, we have to take the radical out of the denominator. We have to multiply by a monomial. That's going to give us 3i on the top. It's going to give us I times I is I squared in the bottom. Then you go back to that chart that hopefully is going to be familiar after we do a bunch of these problems. 3i over I squared is 3i over -1. Can you leave it like that? Sure you can. Could you also write it as -3i and just move the negative to the top? Sure. Do I accept either one? Definitely. They're both right. This one's the more simplified version. I'm sure there are math teachers that would frown at this, but if you've done the hard part, which is rationalizing, then I'm really happy about that. So I'm going to accept either. Let's look at a harder example. So example 7 is going to be 3 over 4 plus I. Actually finishing this problem out, we're going to multiply by, we're going to notice that it has a binomial in the bottom. That's the problem. We need to undo the problem by using the conjugate. So we're going to multiply by 4 minus I, the same thing, but with a different sign. And we have to use it on the top and the bottom. It's only fair if you multiply the top and the bottom by the same number. On the top, I'm going to distribute 12 minus 3i. On the bottom, I'm going to FOIL. 4 times 4 is 16. 4 times -I is -4i. 4 times I is positive 4i. I times negative I is negative I squared. Negative I squared is negative, negative 1, that's positive 1. These middle ones cancel. That's what the conjugate does. It cancels out the I. I squared changes to a number, and now we don't have a radical in the bottom anymore. We have 16 plus 1 is 17. So we have 12, minus 3i over 17. If you get here, I'm overjoyed. I'm like this, really happy. However, complex numbers are supposed to be written separately. So your final answer should be 12 over 17 minus 3i over 17. Because you have a monomial in the denominator, you can split the fractions and say 12 over 17 minus 3i over 17. So this is the best answer. You'll get most credit if you get here, but you'll be a point or two off. You should always write them as separate numbers. So complex numbers are written separately. So this is the exact same rule that we learned in the last section. It applies to imaginary numbers as well. You're either going to multiply by a monomial, like I over I, or you're going to multiply by the conjugate. You're trying to fix the denominator. If the top had said 3 plus 2i, you don't care. It doesn't matter what's in the numerator, you're trying to rationalize the denominator. So you don't use the conjugate for this one, you only use the conjugate for the denominator. That's what you're trying to fix. So your goal is to fix the denominator. You might have to FOIL out the top, but that's just a result of you trying to fix the denominator. All right, and that's basically what we're doing in this section, is learning about imaginary numbers, how to add, subtract, multiply them, but really the goal is to use them in solving equations and finding every root possible. So our goal is to be able to solve equations like this and get to the end where we have imaginary solutions. But these count as the roots or the solutions for the equation given. So we need all the other math to back this up, but this is really our goal. Solve with imaginary numbers. All right, thanks.